Okay, now here is our video on electromagnetic waves. And we've got our first little video here, or first little picture here, electromagnetic waves. All right, there are, as we learned in the last video here, we have 7 types. One of them is visible light, and one of them is ultraviolet light. That's another one. What's funny about that is because ultraviolet's not visible. Haha, there's our little Incredibles meme. Okay, anyway, moving on. Electromagnetic waves, they look like this. They are transverse waves, officially speaking, because they have an electric field component, which is the blue line, and then they have a magnetic field component, which is the red part here. Um, and this is an electromagnetic wave. So you'll notice that they are always in phase with each other. They whatever one is doing, the other is doing as far as going positive or going negative. So in this case, we have our wave propagation, right? The energy is moving to the right toward that plus x axis. But the electric field is oscillating in the plus y minus y, and the magnetic field is oscillating in the plus z minus z axis. So yes, this is in 3 dimensions, and yes, we are bringing back our right-hand rule again. So in our right-hand rule, you can use your pointer finger and go with the electric field. So do that with me right now. Pointer finger up with the electric field. Magnetic field is your middle finger, kind of like in magnetism, right? Middle finger magnet. Um, so your electric field up, pointer finger, middle finger magnetic field, and then the direction your thumb is the direction of energy propagation. So you can see that there. And looking at this, just with our little graphic on the screen, electric field, pointer finger, B field, middle finger, propagation along the direction of the thumb. So those two pictures go nicely together here. To back up just a little bit though, electric field, right? Anytime we have an electric charge that moves, it creates a magnetic field. But then when we have a magnetic field or a moving magnetic field, it creates a force on a charge, which makes it move. But then the moving charge creates a magnetic field, and then back and forth and back and forth. Essentially, it never stops. And that is why electromagnetic waves don't need a medium to transfer them. They don't need a medium because it doesn't matter what material you are in. A changing electric field will always create a changing magnetic field. And a changing magnetic field will always create a changing electric field. So you don't need a medium. You don't need particles. You don't need anything like that to collide with each other. It is simply a matter of the electric field changes, and so does the magnetic field, which makes the electric field change on and on and on forever through all of space. That's how we see stars that are so far away from us, which is really, really cool because it's visible light that just goes through space. And what's fantastic is that they don't die out, right? We can see things that are millions and billions of light years away. And it's all because the electric field and the magnetic field don't die over time. It's just really cool to me. I love space. Anyway, moving forward past this, our next little topic is something that you might have heard generally speaking, polarized light. Right? You have sunglasses, and sunglasses can be polarized, but not all of them are polarized. Some of them are, some of them aren't. The good ones are. The cheapo ones that you get for free at like some college fair or whatever, those are not. Light that comes from the sun is what we call unpolarized, or from a flashlight, from a light bulb, whatever it is. It's called unpolarized. Essentially, that means that you have all of these different orientations of light. And specifically, this is in reference to the electric field. So the electric field we see going here in the plus y and the minus y directions. That's what this polarization is referring to, is the electric field component. So you can see that the E field is, some of them are up and down, some of them are left and right, some of them are at those angles either way. Then they hit this polarizer. So this polarizer. And all of a sudden, out of the vertical polarizer, we only get the E fields that are vertical. And then, let's say that we have a second polarizer here that's horizontal behind it. All of those are horizontal, but we only have vertical light going through to try to hit the horizontal. And does that ever work? No. Vertical things don't pass through horizontal slits. So after that, you would get no light. So I'll challenge you, if you have anything at home that is polarized, and those might be 3D glasses. Some movie theaters use polarized 3D glasses. They don't all anymore because it's almost outdated technology. I hate to say that because it's like the fourth type of 3D technology that I've known. Um, but polarized light, polarized glasses, if you have two polarized sunglasses are always polarized vertically. And I'll talk about why in a moment. Um, they're always polarized vertically. So if you hold one like you're looking through it and then hold the other sunglasses perpendicular to that, you'll have one vertical and one horizontal polarized sunglasses. And if you hold them right next to each other, they should completely black out whatever's behind it because light just can't go through something vertical and then horizontal. It just can't do it. So that's how you can really tell if glasses are polarized or not, is if you have one that you know for sure is polarized, you can just hold it perpendicularly to another pair of sunglasses. And if you see through it, then they're not polarized. If you can't see through it, then they are. Okay, so this is just kind of a recap on what we just said. So unpolarized light means that the electric fields are oscillating every single direction, up, down, left, right, diagonals, whatever it is. Right, there's infinite possible angles, so infinite orientations of the electric field. Remember, the electric field is what's oscillating that we consider to be polarization. And then if we have something that's a narrow enough slit, it's called polarized. Essentially, it needs to be thin enough that one wave's amplitude can't pass through it. So for light, that is absolutely tiny because light has very small amplitudes. Okay, moving on. So this is a direction or a diagram from straight from AP. So you have unpolarized light coming in on the left, and that's how that's just kind of how they draw unpolarized lights going every way. And then it goes through, this is a polarizer. Here's the light coming out from this. So what orientation is this polarizer? I'm hoping you think vertical, right? If we have all of these vertical lines after it, vertical electric fields, this has to be a vertical polarizer. Reminder, electric field oscillation, that's the direction that they have. This next slide, please do not write any of this down because this is not something that you're expected to know. It's just kind of a cool thing that I think is really awesome. If you send unpolarized light through a polarizer, you get half of the light. Essentially, that's because, right, electric field, it's a vector. And essentially, if you have all of the orientations possible, right, the infinite decimal points of angles between 0 and 90 degrees, half of those vector components are vertical and half of those vector components are horizontal. So if you only let through all the vertical ones, then you only get half the light that's still through. So if you ever find something is too bright, then you get a polarizer and then you'll only see half the light. That's part of why we have sunglasses. Because it just basically it dims the light, so it's easier to see. Now that's not all. Essentially, and this is kind of a weird thing. So I realized after my last video that I wanted to keep all my GIFs and everything that moves in the slideshow. So we're doing this back and forth between my note-taking app. I'm going to say that this is the horizon, right? And you drive toward the horizon. And right, if we have a low sun, blah, 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 yada, yada, yada. What do you see at the end here? Kind of toward the end of the horizon, you see something that it just looks like all of this stuff is just like wavy. You can't really see the road. You have no idea what's there. It kind of looks like the road is melting. And this only happens on really hot days. And that's a whole different topic that we won't get into. But that only happens on hot days. Essentially, what happens is when you have low angle light that comes in and bounces off the road, that's what we're seeing. Is we're just seeing all that low angle light that just reflects off the road. The road is at such a low angle and it's at such a high temperature that at a high temperature and a low angle, a lot of things just reflect really well. It doesn't have to be a reflective surface, it doesn't have to be glass, but if you have a low angle and a high temperature, a lot of things reflect. Roads are one of those. But essentially, this is unpolarized light coming in. So all this unpolarized light over here, I'm not going to take the time to draw all the arrows. Well, I guess maybe I am. So we have unpolarized light over here. And when it skips off of this, this is something that you absolutely don't have to know, but I find it so fascinating. You only get the vertical. Oh, I'm sorry. You don't get the vertical. It filters out all the vertical. You only get the horizontals. So you only get all the light that is horizontally polarized. So in this, all the horizontally polarized light, essentially, because it filters out half the information, that's why we can't see everything. Because this horizontally polarized stuff, that's the reflections. All the vertically polarized information, that's what would actually show us the information. Show us where's the horizon, where's the road, where are my lines, are there deer about to cross in front of me, stuff like that. But all these horizontally polarized things make it a lot harder to see because those are the only ones that reflect. The rest of them, they actually, what's weird is they kind of just like the energy plunges into the earth and all the vertically polarized stuff just goes straight into the earth and gets lost forever, which is just weird. But because of all this horizontal polarization here, sunglasses are polarized vertically. So here's your sunglasses. I am terrible at artistry. Here's your sunglasses, and they are polarized vertically because, right, and then they loop over your ears, things like that. Because then it takes out all of this gunk, this information right there. So it kind of just unpolarizes it, and you see only the little fragments that get left behind because no reflection is ever perfect. So you can only see the bits of information that are still there. So sunglasses are polarized vertically just because, simply for the sake of light skimming off the roads and being reflections. So you can get a lot of your information back. If you have vertically polarized sunglasses instead of horizontally, because for final intensity it wouldn't matter, you'd still get half the light's intensity, but that's just the one case where it does matter as far as vertical versus horizontal. Anyway, that's my big old tangent. I digress. Now start taking notes again. Polarizing only happens with transverse waves. You have to remember that. Longitudinal waves, if I had, all right, there's a common fence post analogy. Essentially, you have a rope that goes through the fence posts. But if I have a rope that tries to go through horizontal fence posts, it can't go up and down anymore, so it'll just go sideways. But if I have a slinky, it doesn't matter if I'm vertically polarized or if I'm horizontally polarized. That slinky can move back and forth and oscillate in a longitudinal way. Does not matter what the polarization is. Only thing that matters is that it's a slinky, essentially, that it's a longitudinal wave. So only transverse can be polarized. So here's our nice little fence post analogy. I'll let you pause and take a look at this. One more thing, I will let you pause and take a look at this. We will do an activity in class with this. So, okay, here's a nice little simulation. I do want to just show you a little bit of this simulation here, but then I'll let you pause the video and keep going with this. It is in the slides. Just click on the link right here. This is on slide 13. essentially you can have 3 slits, you can show only 2 slits, or you can show only 1 slit. This is really the 1 slit. Over here you get unpolarized light. Here we have a vertical polarizer. Here, if we go horizontal, you can see there's nothing left. If you're really curious, so that's all AP does. If you're anywhere between vertical and horizontal, you get an in-between amount of transmission. If I'm all the way vertical, I get over here exactly what was before this, because of vertical light, vertical polarizer, it doesn't do anything to it. You can do 2 slits. I'm just going to show you something real fast here, because if we have 1 slit, that's at horizontal, no light. But 2 slits, this is interesting, and this is beyond the scope of AP, but I just find it fascinating. Put it halfway through, and oh look, we went from vertically polarized light to horizontally polarized light. And it's because we have this middle slit, because if we only have 1 slit, there's no transmission there. But if we have another slit that's in the middle, we get a little bit of transmission through the center. AP doesn't do anything more than 2 polarizers. It's just fascinating. I think it's awesome. I love this unit and everything that we get to do with it. And I wish there was more time to explore a little bit more. So AP only ever does 2 polarizers. So 1 polarizer here, another one here. You can kind of explore what you want to do on that. But if you want to just go extra and have some fun, go 2 slits or maybe even 3 slits. See what you can get. All right. Oh, I was already on the right thing here. Okay, next topic. Equations for wave graphs. So you may have noticed, and I will go all the way back to this here. These, as they go up and down, right? Up, down, it kind of looks like what kind of wave? Oh, a sine wave or a cosine wave. AP gives you this on your equation sheet, and it actually comes in the mechanics section. So this is on the second page of your equation sheet. I don't know why they don't put it in the optics and waves for this stuff, but here we are. They give you cosine. Now, as a note, they might use sine, they might use cosine. You have to know the difference between sine and cosine whenever you're writing an equation for a wave graph. And they will have you determine the equation from the graph, or given an equation, determine the graph. Either draw the graph or identify which one in a multiple choice question. These come up all over the place. So it's, remember these 2 things. So you have omega, you have our angular velocity. That is the less helpful way of remembering this. This is the more helpful way. A cosine 2 pi frequency times however much time has passed. And that's the amplitude is capital A. That's just whatever the maximum displacement is. Okay, so write the equation for this graph. I'll let you pause the video here. I'm going to copy this over to my note-taking space so we can take a look at it. But pause the video, try to write the equation for this graph here. See if you can do it before I start. Okay, so here we go. Let's paste this over here. It's thinking really hard. Okay. So on this, we have, so we have our graph. We have A cosine 2 pi f t. Remember that our frequency is equal to 1 over period. So if we want the frequency, all we have to do is just determine our period. Well, starts here at 0, and then the next time it passes through, oh, you might think they're 0.6, but that's not quite true, because this is on its way up, that's on its way down. That can't be the case, so we have to look all the way over here. So 1.2 seconds. So our frequency would just be 1 over our period, which is 1.2 seconds. So frequency, we get 1 over 1.2. I get 0.833 hertz. And units of frequency is hertz Hz. So for us to write this equation, then A, amplitude, this is just how high up it gets. Well, it gets to, oh, I'm sorry. I looked at 1.2 as if that was the normal time, but it's not. It is microseconds. So 1.2 times 10 to the minus 6, which means I will have to take a look at my frequency again. 1.2 e to the minus 6, 1 over that. So I have, oh, it's a very different number. For sure, 833,000 hertz. Very different number. And then my amplitude over here, well, the highest up it gets is 1.5, but it's not just 1.5. It is 1.5 times 10 to the minus 4. And this is our electric field, 1.5 times 10 to the minus 4 volts per meter. So I can say that my electric field is equal to my amplitude, 1.5 times 10 to the minus 4 times the, and this one actually, I know the equation says cosine, but it does need to be sine because it starts at 0 and then goes up. So cosine starts at the top, sine starts at 0. So sine 2 pi frequency 833,000 times t. All right, and you can simplify from there if you want, but that's as far as I'll go. So there's our equation right there for the equation for this graph. So here's the way that AP presents it to you is like this. 1.5 times 10 to the minus 4 sine, and then 5.2 t. That's what they give you there. Okay. Okay, also make sure we pay attention to our axes. So electric field as a function of, oh, this one is of position, not of time. So if it's an electric field as a function of position, what's different is that we can use our wavelength. We can find the wavelength of it instead of the period of oscillation. So it is different. So I'm going to copy this over here. And if you would like to pause the video, try this one out on your own. See if you can solve this one, even though it gives you wavelength here instead. Then absolutely go for it. So pause, try this out. I'm going to start here in just a moment. Okay, so the first thing that I do want to point out is that this one does start up top. So this is going to be a cosine graph as opposed to a sine graph that we were looking at last time. So looking into this amplitude, I get my amplitude is 100. And then cosine of 2 pi f t, the last piece of information we don't have is the frequency. Well, go take a look at your equation sheet and the waves part of your equation. Because frequency is related to something that we can find from a position wave graph. Because the position wave graph, we could say, oh, from here to the top of the next wave, that is what we call a wavelength, or lambda. That's a Greek letter. If you want to see how it's spelled out, lambda looks like that. And essentially, it's kind of like a Y, or I like to look at it like a two-legged brontosaur, kind of. It's got this little head up top, and then you've got little brontosaur legs down there. Anyway, but we can find the wavelength from that. And then AP gives us an equation that lambda is equal to, sorry, not C, V over F. So it's equal to the velocity V over F here. Knowing lambda, we can find our frequency because the velocity of any electromagnetic wave is c. And this is something that is on your equation sheet that is 3 times 10 to the 8th meters per second. It's on your equations, it's on your constants, but this is kind of a number that you, at some point in your schooling, in your college, stuff like that, you're going to have it memorized. 3 times 10 to the 8th meters per second. You don't have to have it memorized for AP, but if you want to go into anything that makes you do physics, you will have to memorize that number. So we can get our wavelength, or I'm sorry, we can get our frequency. So I'm going to say frequency is c over lambda, because c is our velocity, and I've just rearranged those two there. Position is meters. Okay, so this is just a straight up axis, 4 meters. Here is our wavelength, so 3 times 10 to the 8th over 4 meters. If we do that, 3e8 over 4 meters, I get that my frequency is 7.5 times 10 to the 3, 4, 5, 6, 7 hertz. Okay. By the way, a 4 meter wavelength, this is a radio wave. 4 meter wavelength is radio wave. Anything that's in the meters world, oh, and I tell you that right there. Anything in the meters realm is a radio wave. Okay, so now we can take our frequency and plug it in here, and I'm just going to multiply it by 2 pi. So 100 cosine of 2 pi times our frequency, I get 4.71 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 T. 4.71 times 10 to the 8th times our time. Okay, so there's the equation that I get. Here is where it gets a little bit tricky, though. So there's my work put out there. AP, here's the answer that AP gives you, which is kind of a little frustrating, but this is just one of those things that, you know, it's kind of whatever. If it was on a free response, they would take it as a function of time. They wanted it apparently as a function of position, and I got this one wrong because they just were not very clear that they wanted it as a function of position. So yeah, if you want to pause the video and work through my work here, you can see that frequency is there. So frequency turns into c over lambda. Here's the thing, though. C is velocity, t is time. And what's velocity times time? Well, it's distance. So they just took pi over 2 and then turned this into distance of x. And the m it's meters. So they're including their units of newtons per coulomb in the electric field, and they're including their units of meters in pi x over 2 as being their kind of their thing here. I don't like that they did this. That's the only question that I've really seen them do it, but just be aware that it's a possibility for what they could throw at you. I don't think it's likely possibility, but it's a possibility. All right, practice question here. So we have an astronaut who is on the ISS. Send a message in the form of a wave to Earth. Receiver detects the signal transmitted. The graph shows the magnetic field component. Magnetic field component. Okay, make sure you always pay attention to that. I mean, you could have seen that on the graph because it says B in terms of 10 to the minus 8 Teslas versus T in 10 to the minus 15 seconds. Which of the following expressions best represents the electric field? Oh, so I give you the magnetic field and ask for the electric field. Feel free to pause. I'm going to ask you, actually, don't feel free. Please pause. Try to figure out which one of these expressions you think is correct for this question. Once you have your answer ready, let's keep going. So you don't, before when I told you to pause, you don't actually have all the information that you need to solve this question quite yet. You will in this slide. AP doesn't give it to you, and it does frustrate me a lot that they don't give you this equation here. Basically, what AP does expect you to know, though, is that in an EM wave, The electric field and the magnetic field are not the same magnitude. They are related by this equation. The amplitude of the electric field is equal to c, the speed of light, times the amplitude of the magnetic field here. So they're related, but they are not the same number. So AP expects you to be able to see that they're related, but to also be able to see that they're not the same number as each other. So we take a look at this slide then, and we see that our amplitude of our B field is 3 times 10 to the minus 8. Now, what we have to immediately do is say that's the B field. They're asking about the E field. So our amplitude cannot be 3 times 10 to the minus 8. It just can't, because the E field and the B field, they're related, but they're not equal. So all of a sudden we're down to C and we're down to D. So now it's just the difference between a cosine graph and a sine graph. And this one, well, does it start at the origin or does it start at its amplitude? It starts at the amplitude, so answer here is sine. Is cosine. Sorry, letter C, cosine graph. And then here's just your reminder of sine versus cosine. If it starts at the top, it's a cosine. If it starts at 0, it's a sine graph. The equation sheet does only give you cosine, but AP will use sine. They will use cosine. They'll throw whatever they feel like at you just because they can. But, if it starts at 0, sine. If it starts at its positive amplitude, cosine. All right, and that is all I have for you on this video. Please let me know if there are any questions. Otherwise, we'll see you next time. Have a good rest of your day.